if that's there. All right, I can see your screen. I'll turn the time over to David. Thanks so much.
Okay, hi everyone. My name is David Wiseman. Thank you very much for that kind introduction there, Brett. Today I'm going to be showing you around at a high level the RCMCost module within Availability Workbench, just to avoid any ambiguity. Availability Workbench is a suite of software tools, one of which is the module known as RCMCost, so you can see that selected at the top here. Now, Availability Workbench, as I mentioned, is a suite of tools, many of which can share information and work well together in tandem. But for today, I'll just be focusing on RCMCost, the advantages of using RCMCost, and how to actually use it as well. But I'll begin by talking a little bit about what RCMCost is and what are the benefits of using it as a tool as part of your RCM cycle. So RCMCost is a software framework within which you can build a hierarchy that represents your system, its functions, its functional failures, and the causes of those functional failures. And you can populate those failure causes with information about how frequently those failures occur, what you do to correct those failures, what you do to prevent those failures, things like scheduled maintenance, for example. And you can include in there things like lead time on resources, the costs of lost production, the costs of performing your maintenance. Now, the purpose of doing this is that once you've provided the program with enough information, you can then use the software to help you optimize your maintenance strategy, or even select an improved maintenance strategy. And the program does this using a process called Monte Carlo simulation. So essentially what the program is doing is simulating the failures, the repairs, and the maintenance as if they're happening in real time. It can then predict the cost of those failures, and it can try a variety of scenarios, different maintenance frequencies, for example, and advise on which of those maintenance frequencies might provide you with the best results, the lowest cost or the lowest downtime. So you can see on the left here, I've got what we call a functional location hierarchy. This one represents a plastic extrusion plant. So for example, I have a block that represents the extrusion unit, a block that represents a screw feeder. Below that, I can specify what are the functions of a screw feeder, just a description of what that asset does. Beneath each of those functions, I can specify one or more functional failures, a description of how the asset might fail to perform that function. Now, right at the roots of this hierarchy, beneath the functional failures, you have the causes. So, as you may have gathered from what I was saying earlier, the causes are where the bulk of the information go into an RCMCost analysis. Maybe I'll open up one of these for a moment. So in here, you can tell the program about how often you expect your failure to occur, and there are a variety of ways of doing this. I won't muddy the waters by sort of picking through it in detail right now, but here you can tell the program how often the failure occurs. You can tell the program about what you're doing to correct failures when they do occur. How long does it take? What does it cost? What resources do you need? And you can provide similar information about any scheduled maintenance that you're doing. And this could be anything from a scheduled replacement or lubrication, right through to condition monitoring or even fault finding for hidden failures. You can provide the program with that information. And what the program can then do is basically simulate that failure and make a prediction about how much that failure will cost you over the life of the system. But it doesn't stop there. Naturally, you might tell the program, well, for this failure, I'm doing scheduled maintenance every 3 months. But you can ask the program, tell me what might happen if I did that maintenance every 2 weeks, or every 4 weeks, every 6 weeks. You can ask the program to tell you what the cost to your system will be of doing this maintenance across a variety of different maintenance frequencies, and the program can make a recommendation. as we can see here, about how often you should do that maintenance in order to minimize the cost. This can also be done based on downtime if that's your preference. Cost tends to be one of the most frequently used metrics. And as I mentioned, there's a variety of other details that can be included. The effects of failure, what are the impacts? Are there safety impacts? Are there financial impacts? These can be included. The resources, things like spare parts, what does a spare part cost? How many do you need for any given maintenance task? How many fitters, how many electricians, how many engineers do you need to perform a maintenance task? What are the lead times associated with them? And so far, I've kind of focused on one maintenance task. If I'm doing scheduled maintenance against a certain failure, how often should I do it? But in real systems, often it's not really down to individual tasks or individual operations. You're more thinking in terms of maybe maintenance plans, an overarching strategy for a given piece of equipment or even a whole system. For that, there are task groups. This is a facility that will let you group together maintenance tasks and then optimize them as a single strategy altogether. So that might be more consistent with what you're doing in the real world. And there is even a facility called the Bible module, which is included under the RCMCost license, that allows you to analyze historical failure data for a given asset or even a given asset failure mode, and then use the results of that statistical analysis as part of your simulation. So in fact, the simulated failures that you're running in the software should mimic quite closely what you've been observing from your system in the real world. So hopefully, as I've been going through that, the benefits of using a tool like this should be becoming quite apparent. Obviously, the big thing is cost. Minimizing cost by improving your maintenance strategy. A nice way to visualize it is actually on this plot here. So what this plot is showing me, on the x-axis is maintenance interval. How often am I doing this particular maintenance task? And on the y-axis is cost. How much is this failure costing me if I use a given maintenance interval? And the blue trace is the cost. So we can see if I have a very short maintenance interval, I have high cost, I'm over maintaining. On the other hand, if I have a very long maintenance interval, again, high cost because now I'm under maintaining. Failures are becoming more common because I'm not lubricating enough, I'm not replacing frequently enough. So the software is helping you to identify, are you over maintaining, are you under maintaining, and then recommending what the interval is that you should use in order to hit that sweet spot between too much maintenance and not enough, thereby minimizing the cost. But there are other things you can do here too. You probably noticed there's actually a number of different plots going on here. The others, there's like a pink one, a green one, a red one. They represent criticality coming from these effects. You can model not only the impact on cost, but the impact on things like environment, operation, safety, and you can compare these values to limiting, or to limits. So you can say, well, I won't select a maintenance interval if the corresponding criticality falls above a certain level. So you're making sure that, if you do select an improved maintenance interval, you're still meeting with your obligations where things like the safety and the environment are concerned. And other little things you can do here as well, optimize spare parts. One of the problems that people often come across is, obviously I need to have enough spare parts that if there's a failure, I'm not sitting around waiting for new spares to arrive. But on the other hand, what you don't want is to be storing dozens and dozens of spares that you're never going to use, and you spend lots of money looking after them while they sort of rot away in storage. The software lets you model that storage, how many spares you can store, how long it takes to get the parts from storage, and how much it costs to keep them there. And through the spare part optimization, the program helps you to identify how many spares you should store so that you're not storing too many and spending too much on storage costs, but at the same time, you're not storing too few and ending up in a situation where maybe there's a failure, then you have to sit around for a month while the supplier sends you a new one. So there's lots of different things you can get out of this software. I would say the main thing is optimization of your maintenance strategy, picking the ideal maintenance interval for a lubrication or replacement or an inspection. But there are other things too, things like spare part optimization, for example. So from here, what I'd like to do is maybe move on and maybe just build a simple example just to show you how this works. One of the problems we often have is, we can demonstrate this software and we can show people, look, you can do this, this, and this. You can have spares, you can have labor, you can have historical failure data. It's a lot of information to take in, and I think often people worry, well, I don't necessarily have all this information available to me yet. Is the software still going to be useful to me? The answer to that is yes, you can in fact build a functioning model with actually relatively little data, and that's what I'd like to demonstrate here. So what I'll do is maybe start a new project, and we'll begin with the simplest thing, add a location that represents a piece of equipment that I want to model. So I'll add a location. Just as a side note, the program will not limit the number of locations that you can add to your hierarchy. You can have as many as you want to as many different levels of hierarchical structure as you want. Of course, for this example, I'm keeping it very, very simple. So I'll have a piece of equipment. Now I'm going to define the function of that equipment. Anybody sort of familiar with the various RCM procedures out there might kind of recognize this flow where you're defining a function, functional failure, failure cause, and so on. I will just give that a very generic name. I'll call that function. Then this will be the functional failure. And then finally, beneath the functional failure, I will define a cause. Now, for this cause, I'm going to define some failure data. Now, I've said there are various different ways to do it. I'm going to take the simplest route and just specify the failure data manually. So I'm going to say, well, this particular failure is associated with fatigue. That's something I could model using a variable distribution. So I can select that from the drop-down box. I might say, maybe this piece of equipment, if left to just run without maintenance, would have an average life of 1 year before it died from fatigue. A fatigue failure, I guess, often follow a kind of linear increase in failure rate, which I'm going to represent using a shape factor of 2. So I've got on average, it lasts for 1 year, and it will wear out linearly. The failure rate will increase linearly with time. So next, I will go to the maintenance tab, and I'll tell the program a little bit about the repair. So I might say, well, if this fails, it will take 12 hours to repair. I can include lots of information here about resources if I wish. I'm going to assume I'm right at the sort of start of my RCM. I don't really have all of this information to hand yet. So I'm going to stay very simple and just say, if there is a failure, it takes 12 hours to fix it. So I'll click OK. And what I can also do is tell the program, if there is a failure, what is the impact of that failure? That is done through effects. Now, I can define effects externally to the cause using the buttons on the toolbar and then assign them afterwards. But I can also create them through the cause interface as well. That's what I'll do here. So I'll add an effect. I will create a new effect. And I'll just call this something like outage. So it might represent maybe an outage that causes a loss of production. And I can specify what the costs of that loss will be. I can have cost per occurrence and cost rate. Maybe with something like production losses, a cost rate is kind of more appropriate. So that represents maybe how much it costs you for every hour that you're out of service, maybe lost barrels of oil, or lost vehicles coming off a production line. So I'll click OK to create that effect. I can even tell the program what types of outage the effect applies to. Again, for the purposes of simplicity, I will assume this outage or this effect only applies to failure. So I'll click OK. And there we have an effect. And it only applies to corrective outages, to failures. Now, again, an individual cause potentially can have multiple effects, and there's no problem with me having more than one effect here. But for simplicity, I'll just stick to one. So now let's go back to the maintenance tab and tell the program a little bit about what we're doing to prevent that outage. So I might go to planned maintenance and add a new planned maintenance task. So I can tell the program, for one thing, how often that task takes place. Maybe I'll stick with 1 year. I'll say I'm doing this maintenance every year in order to try and prevent outages and losses of production. And of course, I can tell the program how long that maintenance takes and even provide an operational cost. I might say this particular maintenance is going to cost me, let's say, 1,000 every time I do it. Now, obviously, again, I can break that cost down. I could even, granulate it down to the point of having different labor categories, different tools that they're using, different spares. But here, I'm just lumping it all together in my operational cost. So again, for the purposes of simplicity. So I click OK. And now I've got a corrective maintenance and a PM, failure data effects. If I click OK, there's my cause. Now, at this point, I might want to try to optimize my maintenance. There are a couple of ways to approach that. For visual purposes, I'm going to do it through the cause dialog. We've already seen that you can show the optimization plot on the right here, but I'll see more information if I do it this way. I'll open up the cause, go to the strategy tab, and at the bottom here, I can ask the program to simulate this failure. Now, in the options, I can tell the program about how many simulations to do and what the lifetime is. Let's assume that we'll stick with the default lifetime, which is 10 years, and the default number of simulations, which is 100. That can be increased, of course, but for now, we'll just keep it as it is. So we'll do those simulations of this failure. And you can see the program generates a few different metrics, things like cost, downtime, downtime by failure or PM, number of maintenance tasks. The thing I'm most interested in here, though, is here, the cost-benefit ratio. This is the ratio between the cost of this cause with the current maintenance strategy in place, which is this value, against the cost of simply running to failure. Naturally, I want that value to be less than 1 because it implies that the cost of doing the maintenance is less than the cost of not doing it. So my maintenance is worthwhile because you can see the CBR, cost-benefit ratio, is less than 1, but maybe we can improve on that. So let's hit interval optimization. And with this button here, I can tell the program what maintenance intervals to try. So I'm going to try doing maybe 50 different maintenance intervals, maybe at increments of 1 week. So I'm going to do this in hours. You can actually use any time unit you want as long as you're consistent throughout the program. I'm doing everything in hours, so I'm going to try 50 intervals. So I'm going to try doing the maintenance every week. Then I'll try doing it every 2 weeks. Then I'll try doing it every 3 weeks. Hopefully, the program will be able to tell me what's the ideal frequency for the maintenance. If not, maybe I can adjust the intervals and get a slightly better result. So let's click OK and run that analysis. So you can see it's working its way through at the bottom here. And it's giving me this curve. Now, it's a little bit lumpy. That's only because I've got relatively few simulations. If I bumped up the simulations to 10,000 or 100,000, that would smooth out. But let's accept that recommendation. So that's now updated the interval. So that's mathematics, let's say 6 or 7 weeks or something like that. And we just run that quickly. And you can see the cost benefit ratio has dropped appreciably. Now, from being about 76% of the cost of running to failure, it's dropped to maybe only 16%. So that's a massive improvement on what we had before. So not only is the program able to make a recommendation about how frequently to do the maintenance, it can actually quantify how much better it might be than the intervals you've been using previously. And again, it doesn't stop there. If I wanted to, I could say, well, what if I did condition monitoring instead? I could go to the maintenance tab and create an inspection. And I could say, this inspection takes half an hour. This only costs maybe 500 as opposed to the 1,000 cost by the corrective maintenance, the preventative maintenance. And I can also specify predictive data. I can say that I can pick up this potential failure up to 2 months in advance of a functional failure of the system. And the probability of detection during that time is maybe 99%. Then, for the PM, I can tell the program this is a secondary action task. So if I do an inspection and find a problem, I can trigger the PM to prevent that problem from turning into a failure. So we go back to the strategy tab. We will turn off the planned maintenance task. So now it is only ever triggered by the inspection. Maybe I will optimize the inspection. Let's do something similar to what we did before. Just test the same intervals, run it again. So this is saying, do the inspection at roughly the same sort of interval that we saw for the preventative maintenance. We can accept that, run the analysis again, and now we can see the cost benefit ratio has dropped even further. So not only can we try to optimize the maintenance we're doing, we can even test that against potential alternatives. So here you can see we're doing an inspection, and we've tested that and found maybe this is a better option than doing planned maintenance. And we can try out things like alarms, commissioning, the cost of redesigning the system. All of these things can be folded into your analysis. So that is a simple example of how you can use RCMCost, and hopefully that's demonstrated the kind of main thrust of the software, helping you to optimize an existing strategy, or even helping you to select an alternative, even better strategy. And again, that last point of just about, you don't need a huge amount of data to get started. As I've shown you there, you can actually start with relatively simple data. Then later on, as better data becomes available, you can just layer that onto your analysis and just see how that affects the recommendations. So I think that was everything I was going to talk about with regards to RCMCost. Yeah, if I can hand back to you, Brett, and if you have any questions or any comments you wanted to add.
No, I appreciate it. That's a great overview, and like David said, it goes into even more in-depth analysis. And so if you have questions, you want to dig in a little bit deeper, let us know. One question I did have for you, David, is what's the best way for someone to bring some data in? Maybe they have it in from another program, Excel, to help facilitate some of the information here.
Well, there are a variety of options available, starting from things that are relatively straightforward, going right through to much more, I guess, large-scale solutions. Standard part of the tool are the import and export facilities that you'll find in the File menu. If we click on Import, you'll see there just a short list of the import formats that we support. So you can pull data from Excel, from Access, SQL Server. So for example, if you've been given a bill of materials, a list of spare parts, for example, as an Excel worksheet, you can just pull that directly into the software via the import facility, and it saves you the tedious job of entering that information by hand. Now, sort of towards the other end of the scale, if you're using a big ERP system, something like SAP or Maximo, we have portal facilities that are available that let you connect directly to those systems and download information that can then be used as part of your RCM cost analysis. So for SAP, for example, you can pull down your location hierarchy and causes, labor and spares, your maintenance plans. You can use RCMcost then to optimize those maintenance plans, and then, if you wish, upload the improved plans or upload new plans back to SAP. And similar facilities are available for Maximo as well.
Fantastic. I appreciate you covering that as well. Let me just switch back to my screen here just quickly. And like I mentioned before, if you want additional training, additional questions, come up through the process of using our software, you can actually download a free demo of RCMcost. It's through the availability workbench. It's that long URL there at the bottom, or you can go to Isograph and go under products and select that. But download the free trial, play around with it, and then make sure to contact us so we can answer any questions that you come up against. We really appreciate your time today, and thank you, David, for sharing this with us. And I appreciate everyone's time. Everyone have a great remainder of their day.
Okay, no problem at all.
Thanks, everyone.
Bye now.
Bye.